Hello, good evening everyone. Welcome to the week 7 tutorial session for this course digital signal processing and its application. So today we are going to discuss the problems based on the week 7 lectures, and this video will be uploaded on YouTube as well. So if anyone missed the lecture now can watch it later on YouTube, and also you can comment in YouTube section, and there we can reply. So coming to the first question of today. So what are the advantages of using IIR filters for digital filter design? So basically the IIR filter offers very low complexity and requires lesser computation in general. So what are the two advantages? That it requires low complexity. So option C is correct, and then requires lesser computation in general. So in IIR filter, first thing is that it has a very lower complexity. Second thing is require less computation in general. Okay. On the same hand, FIR filter, we'll see the advantage of FIR filter also. It offers like very good stability, okay, and desired phase response. But on the same hand, it is like more complex and require more computation. So we'll move on to the second question. So which statement is correct for the following transformation? S is equal to log z. Assume that the imaginary part of log z lies in between -5 up to +5. So the transform here is S is equal to log z and z is equal to a e to the power of j omega. So S will become, like when you substitute z equal to a e to the power of j omega, then it will become log a plus j omega. So from this we can see that in option A, like for every z complex z, there is a unique representation in the form of a e to the power of j omega. So mapping is one-to-one mapping from z domain to s domain. So option A is correct. Now for option B, like here you can write for every z, there is a unique representation. So it will be a one-to-one mapping. in the form of a e to the power of j omega, and here omega is in between minus pi to plus pi. Now coming to the option B, like for omega in minus pi to pi, the imaginary of s uh, is also in pi to pi, hence a circle in the z plane defined by mod z is equal to a would translate to a finite line segment in the s plane. Okay, so the option B is incorrect because it is written each circle in z plane is mapped to an infinite line in s plane. But for B option, the circle defined by mod z is equal to a would translate to a finite line segment in the S plane. Now coming to the option number C, for option C, what it says, the interior of the Z is equal to 1 is mapped to a subset of the region. Real part of S is less than 0. So when A is less than 1, this is implied that log A is less than 0. Hence, real part of S is less than 0. So the option C is also correct. Now the entire S plane is covered by the transform. So like the entire S plane is not covered by the given transform. So option D is incorrect. So for question number 2, for this question, the option A and option C are the correct options. So now we'll move on to the next question. So in this question for the transform S is equal to 1 minus Z inverse by 1 plus Z inverse, map the points given in the following figure in Z plane to S plane. The circle shown in the figure is mod Z is equal to 1, that is the radius of the circle is 1. Choose the correct option from the corresponding point in the S plane. So like here you can see there are 4 points A, B and C, D. Now we have to find where this corresponds into the S plane, and the options are given. So for Z is equal to e to the power of j omega, our S will become j tan omega by 2. And the transformation from like analog frequency to the digital frequency is given by omega is equal to tan omega by 2. Now for each omega is equal to its angle in the interval between minus pi to plus pi with the positive real axis. Since above transformation is like monotonically increasing, the order which will follow will be D is less than B, B is less than C, and C is less than A. In this order, it will follow. So, and this will be observed on which line? Imaginary of S is equal to 0. So, that is on the y-axis. So, here which option looks correct? So, the A should be at the top, and after that C. So, option A looks correct here. So, now we will move on to the question number 4. So for z, like consider transform S is equal to 1 plus z inverse z to the power of minus 2 divided by 1 plus z to the power of minus 2, and the corresponding frequency transform from the continuous time filter frequency uh, to the discrete time filter frequency omega. Which of these statements are correct? So for z is equal to e to the power of j omega, we have S is equal to j tan omega. And the frequency transformation is from the continuous to digital is omega is equal to tan of digital frequency is omega. Discrete time filter frequency. Now, here our discrete time frequency is lying in between minus pi to pi, and it won't take the value of minus pi by 2 and pi by 2, because on that value the tan is not defined. So for this equation, we can see that like as it is not completely defined, the mapping from discrete to continuous is 1 to 1, so this option is wrong. The mapping from discrete to continuous is monotonic, this is also wrong because there are two discontinuities here. So we can also write S is equal to sigma plus j omega. So here our z squared will become like this. So from here we can see that mod, like it maps mod of z is greater than 1 to real part of s is greater than 0, and mod of z is less than 1 to real part of s less than 0. Yes, option A is correct in this question. Again, C will be incorrect as inverse mapping does not exist from S to Z. Coming to the question number 5. Why can't a real filter have a pass band of constant magnitude? Like a constant pass band implies that the frequency response has infinite roots. Like let's suppose for some real number C, which is not possible for a rational filter function, except for all pass filter. So this implies that Hz has infinite root. Okay, so which is not possible for a rational filter function, except for the all-pass filter. So, which option is correct? Correct. The filter becomes irrational. Yes, option C is the correct. An analog filter. I will move to the question number 6. An analog filter designed using some or all of L, C, and R elements is guaranteed to be which of the following: rational, causal, stable, and having an impulse response with a finite suppose. So the filter designed using LCR element is guaranteed to be rational and causal. However, a filter having only inductance and capacitance may be unstable, and also the impulse response of such filter will have infinite support. So, filter designed using LCR will be guaranteed to be rational and causal. On the other hand, designed using only an L and C, it may be unstable. So, option A and B is correct for this question. Coming to the next question. Which of the following is true about the FIR realization of a filter? So an FIR filter is a filter which like there is no feedback in its equation, which makes the filter inherently stable. So in FIR there is no feedback, makes it stable. So they are always stable. Option C is correct for this question. Now coming to the question number 8. Map the S plane in column A onto the Z plane in column B using bilinear transformation. So the left hand plane of the S plane is mapped to the area inside the unit circle of the Z plane. So the left half plane will be matched to the inside the unit circle. Okay, left hand plane of S plane will map to area inside the unit circle of Z plane. Okay, so for 1 it is C, 1 it is 3, and we also know that the imaginary axis is mapped onto the unit circle. So the imaginary axis is mapped to the unit circle. So 2 corresponds to the 1, 2 matches with 1. Now for 3, which will be the option? The right hand plane that is outside the unit circle. So for 3, it is 2. So which option is correct? 3, 1, 2. Option D is the correct answer for this question. Coming to question number 9. In the given figure, choose the realizable filters. So the realistic aspects of the specification of a filter are like See, the pass band cannot be flat, so these things we need to check. It cannot be flat, means tolerance is a must. Same for a stop band, can't be flat, tolerance should be there. And now transition band must be of non-zero width, must be of non-zero width. And also the frequency response of this filter must be an even function so that impulse response is real. So frequency response of the filter must be even function so that impulse response is real. Okay. So after considering all these points, which option is correct? See, in option A, again the transition band is completely like of non-zero width. So option A is wrong. Coming to option B, it looks correct because the pass band is having some tolerance and transition is also non-zero width. So option B is the correct answer. Now again option C, there is no tolerance here. So this is again wrong. And option D also there is no tolerance. So option D is also wrong. So correct answer is option number B for this question. So which of the following remain unchanged on applying the bilinear transform? So for bilinear transform on the frequency from continuous to the discrete domain is given by omega is equal to tan omega by 2. So due to the like uh, monotonicity of the target function, the nature of the filter in the analog domain is preserved in the discrete domain. So there, that is a low pass analog filter. So there will be low pass, band pass, or high pass. And also like the transformation is only on frequency domain. So uh, like only on the frequency axis. So there will be like the magnitudes are not transformed. So magnitude are not transformed. Okay. So therefore the passband and stop band tolerance do not changes. So option B is also correct. Also the nature of passband and stop band do not changes. And as the frequency axis is transformed, the width of the transition band will change. So width of transition band will only change. Remaining other all three options will not change. Why? Because as the frequency axis is transformed. Now coming to question number 11. For a Butterworth filter, what is the nature of pass band, stop band respectively? So for Butterworth filter, the nature of both the pass band and stop band is monotonic, that is strictly either increasing or decreasing magnitude. So option A is the correct answer. Both the pass band and stop band will be monotonic. So now we'll see little about the Butterworth filter. So a Butterworth function of order k is defined by so Butterworth function of order k is defined by mod of h omega is equal to 1 by 1 plus omega by omega c to the power of 2k. Here k is equal to 1 to 3. And a filter so designed is referred to a Butterworth filter of order k, and the parameter omega c is the here cutoff frequency of the filter. So here k is the order of the filter. So here k is the order of the filter. Omega c is the cutoff frequency of this filter. So for described value of tolerance parameters, that is epsilon and delta. So what is epsilon and delta? First we will see that. So first we will see the tolerance diagram. In tolerance diagram, let's suppose this is the magnitude response h of j omega, and let's suppose that is a low pass filter here. There is some transition band, and then this is our stop band. So up to here it is a pass band, and this is our stop band. Okay, this is the omega p. To this it is passed, and this is the omega s, that is the stop band frequency. From after this omega s, the signal will be stopped. And so this is our transition band. First I will draw for the pass band. So what is this? This is our transition band. And this value, this is delta. Okay. And this is 1 minus epsilon. So here, uh, this epsilon and delta are the tolerance parameters. And this is tolerance diagram of low pass filter. So what is the pass band and stop band cutoff frequency? Omega p. The pass band cutoff frequency. So what is omega p? This is given as omega c into epsilon by 1 minus epsilon to the power of 1 by 2k. And the cutoff, like stop band cutoff frequency is given as omega c 1 minus delta divided by delta to the power of 1 by 2k. So to design an analog filter, we need to know the transfer function hs expressed as a function of complex variable s. So given the Butterworth function here, how do we find the corresponding like we have to find the corresponding transfer function. So actually here it will be mod square. So we know that h of s and h of minus s is equal to j omega is equal to mod of h of j omega square. So in the equation it is already given. So omega is equal to s by j. Let's take like now they substitute this value. So our h of s and h of minus s will become 1 by 1 plus and omega is equal to s by j. So it will be s by j omega c to the power of 2k. Okay. So we need to know like the transfer function hs to design an analog filter. So now, so the roots of the denominator polynomial are located at the following points in the S-plane. So roots are located at S is equal to j omega c minus 1 to the power of 1 by 2k. Okay. So this will become omega c e to the power of, you can write j into minus 1 to the power 1 by 2k as e to the power of j pi 2k plus 1 by 2k for k is equal to 0, 1, 2 dot dot 2k minus 1. So the poles of this hs into h of minus s, that is mod of like magnitude of h j omega square It forms a symmetrical patterns on the circle of radius omega c. It forms a symmetrical pattern on a circle of radius omega c. So from here, it you can write poles. Okay. So now coming to the question number 12. Does omega c lie between omega p and omega s for a Butterworth filter? So this is not necessary. Like omega c is just the half power point. For example, if the passband tolerance was greater than the half power, then omega c would lie in the passband. So one cannot comment like on the location of omega c. So it will be not necessary. So omega c, the half power point. So what is half power point means? Like if the tolerance was greater than half power, if the tolerance is greater than half power, then omega c would lie in the passband. Okay. So which of the following are true for a Butterworth filter with order n and cutoff frequency omega c, where omega p is the passband edge and omega s is the stopband edge. Kp is the passband gain and Ks is the stopband gain, and the gains are in units of dB. So here h of j omega is given by 1 by 1 plus omega by omega c to the power of 2 of 2n. So here gain k is equal to 20 log mod of the magnitude of h of j omega. So k is equal to minus 10 log 1 plus omega by omega c to the power of 2n. Okay. So omega by omega c to the power of 2n. This will become minus k by 10. So 10 to the power of minus k by 10. And this one will go that side. So it will become minus. So at pass band, k is greater than kp is implied that omega p by omega c to the power of 2n is less than equal to 10 to the power of minus kp by 10 minus 1, and at a stop band k is less than ks. So omega p by omega c, sorry, omega s here is a stop band. to the power of 2n is greater than equal to 10 to the power of minus ks by 10 minus 1. So option B is the correct option for C. Omega p by omega c 2n is less than minus 10 to the power of minus kp by 10 minus 1. And for omega s by omega c to the power of 2n is greater than, option D is the correct answer for this question. Now, which of this is allowed value for the cutoff frequency of a Butterworth filter with a minimum passband gain of, like minimum passband gain of kp is equal to minus 1 dB at passband cutoff frequency is 4 radian per second, and the maximum stop band ks is equal to minus 20 dB at omega s is equal to 8 radian per second. Okay, so as we have seen before that for passband frequency is less than equal to 10 to the power of minus kp by 10 minus 1, and for stop band frequency it will be greater than equal to, this way we can write like we will first transform the power 2n onto the left hand side, so it will be 1 by 2n, then shift omega c to the other hand side. So similarly we can write this is less than equal to omega s divided by 10 to the power of minus, sorry, ks divided by 10 minus 1 to the power of 1 by 2. So n is greater than equal to log 10 to the power of minus kp by 10 minus 1 minus log 10 to the power minus ks by 10 minus 1 divided by 2 log omega p by omega s. So we can substitute all the value. We have omega p, omega s, kp and ks. And after substituting all the value, we will get n is greater than equal to 4.289. Like this value will be 4.289. So to ensure the stop band tolerance requirements are met, we choose the smallest integer greater than this value. So our capital N is equal to 5. And by substituting this cutoff frequency inequality, we get, like when you substitute N is equal to 5, and now you give in this equation, in equation 1, then we will get 4.57 radian per second is less than equal to omega c, that is less than equal to 5.05 radian per second. And so like the valid choice here is option number C, that is equal to 5 radian per second. So now let's take one more question. Determine the transfer function. So I will write the question with Here only direct. Of a Butterworth filter of the low pass type of order k is equal to 3. So assume that 3 dB cutoff frequency omega c is equal to 1. So now we have to determine the transfer function. So this question, so for filter order k is equal to 3, number of poles is equal to 2k, that is equal to 6. So and these are located on a circle of unit circle with the angular spacing of 60 degree. Okay. So now if it is 6 pole, so now it will be located at the this is the first pole, second pole, third pole, fourth pole, sorry, fifth pole and sixth pole. So each are located at the angle of 60 degree. Okay, and this is our omega c. This is the real plane and this is the S plane. This is our imaginary axis. And here it is j of omega c. Okay, and this side is minus of j omega c. So now if you take the value, s will become minus half plus j root 3 by 2, and one s is at minus 1 and another s is at minus half minus j root 3 by 2. Okay, so these all are the left hand poles to the SS. So these are left hand pole. You can see this one is the pole which is minus half uh, plus j root 3 by 2, and this is our minus 1, and again this is our minus half minus j root 3 by 2. So the transfer function of a Butterworth filter of order 3 is therefore Hs is equal to, we have to just write all the equation here. So s plus 1 into s plus half minus j root 3 by 2. This was the pole in the upper side. And now s plus half plus j root 3 by 2. So after multiplication, we will get 1 by s plus 1, and this will become s plus half squared minus j root 3 by 2 squared. So we will get 1 by s plus 1 s squared plus s plus 1. So this will get, and finally we will get the transfer function as s cube plus 2s square plus 2s plus 1. So this is our final transfer function. Now, the for transfer function uh, modified for a Butterworth filter of order 3 and cutoff frequency omega c. What it will be? Hs is equal to 1 by, we have to substitute s by omega c to the power of 3 plus 2 into s by omega c square plus 2 into s by omega c plus 1. So we have to first assume that omega c is 1 radian per second and find out the transfer function of the required order. And then to find the transfer function of given omega c, we have to replace s by. So we have to replace s by omega c in the transfer function obtained in the step 1. Earlier, omega c was considered as 1 radian per second. Okay. So for today, we'll end the lecture here only. If you have any doubt, you can ask. And also, this video is recorded and it will be uploaded on the YouTube, and the link will be provided in the portal. And you can watch this later also if you could not join now. And then if you have any doubt, then you can ask in the forum or in the YouTube comment section. So thank you everyone. We'll again meet on the next week at the same timing, 7 p.m. to 9 p.m. So thank you. Bye bye. So I will end the lecture here only now.